All right, let's talk about isomers. That is this thing that we've sort of alluded to about how you can actually connect these in some different ways. So isomers are going to be defined as molecules that have the same formula, so same number of carbons, same number of hydrogens, but different, what we say, connectivity, meaning how the atoms are connected to each other. So we're essentially going to pull carbons apart in the carbon chain and connect them in a different way. Now, one way that I think makes it a little bit easier to see these is to actually take all the hydrogens off and only look at the carbon chains. Now, this is not a correct way to write a structure, but it's a good kind of starting point. So if we look at butane, go up and look at butane. That's the structure of butane. So let's focus on just these 3 carbons in a row. Or the 4 carbons in a row. Ignore the hydrogens for now. Now we're going to ask, are there ways that we can write this where the carbons are actually connected to each other in a different way? Now the first thing I want to show you is the most commonly wrong way to do this. And that is like this. All right. The reason this is wrong is that this is actually the same. Single bonds can rotate. And we know that, based on what we talked about before with the geometry, that the geometry of a 4-carbon chain is not straight anyway. It's actually kind of zigzag. So to say that we just kind of move one down here, all we've really done is rotate something. We haven't actually changed the way these are connected. Another way to think about that is to think about how the ordering of the chain. So in this case, we could order from left to right 1, 2, 3, 4 carbons together in a chain. We still have that same ordering here. 1, 2, 3, 4. So this is not an isomer. So then let me show you what is an isomer and how we can tell that it's different. There's only one other isomer of butane, and that's this one. If we put that 4th carbon as coming off of the middle, or the 2nd carbon instead of the 3rd, now we have something different. There's nothing we can do to twist this or bend it or move it, kind of bend it around to make that into the beginning one. We'd have to actually disconnect one carbon and stick it on somewhere else. And that's why this is now an isomer. So now let's add the hydrogens on here. And the hydrogens can also be a good clue to whether or not you have isomers, because you can look at how many are on each carbon. So in this case, we've got a CH3, CH2, CH2, CH3. And that's going to be the same here. I won't write out all the H's, but you get the same idea. CH3, CH2, CH2, CH3. Now here is a little bit different. Remember, we have to have 4 bonds per carbon. So this one needs 3 more. How many more does this one need? 1. And then 3 here. And 3 here. So if you count up all those hydrogens, there are still 10, just like in the first structure. but that one is a different connectivity. The carbons are connected to each other in a different way. Right. Instead of CH3, CH2, CH2, CH3, you have CH3, CH, CH3, and then another CH3 connected to that CH. So that's what we call an isomer. Now, if we write a condensed structure of this isomer, it's going to get a little bit trickier because we can't just say CH3, CH, CH3, CH, because that makes it seem like the CH is going to be on the end, when actually we know it's coming off of the middle. So when we write a condensed structure of something like this, there's a couple ways we can use, a couple things we can do. I think the easiest way is to actually just keep the lines in there and only condense the hydrogens. Then we can clearly see how everything's connected. One way that this is written as a condensed structure just in a straight line is like this. So the way we deal with this problem of having these things connected is we recognize that there are actually two CH3s, so two of the same thing, connected off this one. So we can use parentheses, kind of like we did with formulas, and say, all right, this CH3 is coming off, and then there's another one. So the parentheses tell us that thing is actually stuck to that middle one, not in a straight line, not just connected on a straight line. The other way we know that it's not just connected in a straight line here is that that carbon would have too many bonds, and then the CH wouldn't have enough. We just put them all in a line. If you ever see a CH3 with a bond on either side, you know something's wrong, because that carbon now has 5 bonds, and that can't be possible. All right, so let's practice this now with some of the others. Let's look for isomers of pentane. So I'll give you one. This one. The one we already talked about where they're all in a line. But you should be able to find two more ways to connect those carbons that are different from them all being connected in a line like that. And just bending them, even if it's very zigzag, is not enough. You have to find a different way to connect them. If you think you found one, talk to somebody around you, and then see maybe they found a different one, and try to think about if that's valid, if it is actually something different or not. Anybody find any yet? I know you found one, right? You find the other one too? Maybe? Anybody think they got one? All right, if you think you got one, let's put it up on the board over here so we can see. Anything you think you've got. You don't have to be too certain about it. But if you think you got something different, come put it up on the board so we can all see. And we'll see if we can find them.
Like,
Okay. Mm-hmm. Yeah. Yeah. All right, what do you think about this one?
it looks better on the paper than on the board.
Well, we don't care so much about how it looks, but let's see if it fits the rules. What? You think you got one too? All right.
Well, I'll still write it down. It's probably this one.
Oh, okay. You don't want to put it up on the board?
I'll put it up on the board, whatever. This one.
Try it.
Yes or no?
No, but
Okay,
but it's a
fine.
good example. I'd like
Alright.
to see it.
Is mine yes or no?
Yes. Yours is a yes. So that's a good one. Why does this one work? Well, Nathan's writing. Go ahead, keep writing. We'll keep talking about this one. Why does that work? Why is that an isomer? Why is it an isomer? Why does it answer the question? Why is it an isomer of pentane?
Is this one is going to be connected to the hydrogen in the three different angles? No, it's connected to the other carbon.
From the formula of
Mhm.
contains, and the connectivity, the C, all the C's still have the same amount of hydrogen,
Mm-hmm.
just like if you had to build a chain of C's.
Right.
So they have the same number of hydrogen.
Right. So we look back at this definition, same formula, but different connectivity. This example is still, so if we put in all our hydrogens here, that's C5H12. So this example here, which I'll put down in the notes, I'll write it as a condensed here, just to make it a little easier. This is also C5H12. So it also has 5 carbons and 12 hydrogens. But it's definitely connected in a different way. If we look at the longest continuous chain here is 1, 2, 3, 4, 5. The longest continuous chain here is 1, 2, 3, or 1, 2, 3, or 1, 2. However you count it out, you can only get 3 carbons and then you stop. And the other 2 carbons are sort of coming off of it in a different way. So this one's definitely connected in a different way. We also have a carbon that has no hydrogens on it in the middle, where there's nothing over here. So same formula, but connected in a different way. So definitely an isomer. All right, let's look at the other one here.
Where are the hydrogens, first of all?
Well, he was being lazy and not drawing them out. But also, I think that's where you notice where you went wrong also, right? Because if you do draw the hydrogens out here, how many hydrogens do I have? 10. And there's no room for any more, right? So that can't be an isomer. What if I just take off one of these and put 2 extra hydrogens on there? Does that work? What's wrong with that? There's another reason this is not an isomer. I've fixed the formula now. This is C5H12, but it's not an isomer. Why not?
The chain of
Yeah.
carbons here are 3 here and 5, and the H inside, like the bond in the middle.
Yeah. Yeah, sure. I mean, it looks a little messy, but let's assume that it's okay to be like that. There's a bigger issue here. Remember, isomers have to fulfill 2 criteria. It has to be the same formula, has to be different connectivity.
Can the 2 hydrogens be right next to each other?
They can, but in this case, the problem is that this is the same as this. Everything's connected in the same way. It's just kind of bent over on itself.
Because if you were to look at it from the side.
It looks different, but yeah, if you imagine taking this carbon and sort of stretching it all out, then you'd have CH3, CH2, 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 CH3, just like this.
Yeah, it's kind of like this one, the first example is that not an isomer.
Right. So this is the same example as up here, where it's just kind of bent over, which makes it not an isomer because it is the same as this one, not a different structure. There's still one more. Can anybody find one more now that we've talked about it a little bit more? There's one more isomer that has the same formula but a different connectivity. We found this one, we found this one, and then there should be one more. See if you can find it. So I know what you mean. Okay, what do you think about this?
Yeah, the triangle.
is it, first of all, does it have the same formula? And is it connected in a different way?
Yeah.
How do you know? If I asked you what is different about that from, let's say, this first one, well, what would you say?
From mine or from that?
Either.
The two carbons are sitting, well, the three carbons are more of like the base with the three hydrogens around it. There's three hydrogens around the last corners of the carbons,
Mm-hmm.
and then the rest,
There's one carbon that only has one hydrogen atom.
Yeah, so that's a good, and then another way we could say it, all those are correct. And we could also talk about how this is like a chain of 4 carbons. The longest continuous chain is 4, with another one coming off of the second one. And none of these really fit that description. This, we might say, is a chain of 3, with 2 more coming off the middle one. And the first one we might say is a chain of 5 all in a row. So those are other ways that we could distinguish them from each other. So yeah, you're correct. There's the other isomer would be like this. You could also write 4 carbons in a row like this with the second one coming off the second carbon. Now, as these things get bigger, it becomes easier to come up with a few isomers because there are more. The more carbons you have, the more possibilities. But it becomes very difficult to actually find all of them. So we'll maybe get into that. Our next part, I think what we'll stop at for today, after we do this and kind of talk about these, is how to name alkanes. That was a nice groan. I like the enthusiasm. Naming alkanes. All right.
is this gonna be on the test?
Yes.
That's reassuring.
So that's the first part, is you always just name it with ane. So that makes sense. The trick with alkanes is not a trick, but the thing that makes naming them sometimes tricky is that we have to think about what sorts of things are attached to the alkane. So first, when you have just a regular straight chain, the name is just the name that we already went over. So if I give you something like this, you say, okay, that's 4 carbons in a row. That's called, anybody remember? Butane. That's it for that one. That's its name, butane. So our first step is always going to be to find the longest continuous carbon chain. And if that's it, then that's it. So if the longest chain encompasses all the atoms in the molecule, then you're done. The longest chain is butane, you're done. Let's say, though, instead you have something like this. So the longest continuous chain is how many carbons in a row? Well, there are 5 total carbons in the molecule, but how many are in a continuous chain? Just 4. You can count it a few different ways. You can say 1, 2, 3, 4, or you can say 1, 2, 3, 4, or 1, 2, 3, 4. You see how I'm doing that? So how many are connected to each other in a row? And just because it's more obvious in this case, we'll just start from left to right and go like that. So this is also going to be butane, but not just butane. Because we also have to account, for this thing that's hanging off of the chain. Now, things that are hanging off the chains are called substituents, meaning that they're substituting for hydrogen. So we have a substituent that is 1 carbon. And a 1 carbon substituent is always going to be called methyl. So meth always means 1 carbon, like methane. This isn't methane because methane is a molecule by itself. This is a carbon that's hanging off another chain. So we call that methyl. We put a YL on there instead. And so we put that in front of the other name. So this is methylbutane. But we're not quite done yet, because we have to specify where on the chain that substituent is. Otherwise, we may, well, in this case it doesn't matter, but in other molecules, we may be drawing the wrong one. There may be multiple different ways to write a methylbutane. So we look at how many carbons on the chain it is. In this case, it's on the second one. You see that coming off the second carbon? So the correct name for this compound is 2-methylbutane. So the butane comes from the 4 carbons in the continuous chain. Then we have this extra carbon hanging off there. It's just 1, so it's called methyl. And it's coming off of the second carbon, so it's 2-methylbutane. The 2 comes from the second carbon, and the methyl comes from that it's methyl.
So when you're adding the second methyl to,
Mm-hmm.
when you're adding the methyl to the second butane, is that just for naming methylbutane?
Right, so this
Otherwise,
is not,
We wouldn't just have methyl hanging off of the butane too, would it?
well, this is a different molecule.
Okay.
So yeah, this is butane, and this is 2-methylbutane. Those are different molecules. They have different formulas. This is actually an isomer of pentane. It's that one on the right. It would also be called 2-methylbutane. All right, so let's put this into some kind of rules here. Yeah.
So if you want to ask a question like, count the numbers of the carbon chain.
Yeah.
You're not supposed to count the one on the bottom, right?
Right. The longest chain is the ones that are connected together in a line. Yeah.
Then my question is now is, if we have like a formula which has something like that's the T shape
Yeah.
upside
Right.
down, might of the square
So where would the chain
is gonna be
would be like this,
okay.
because those are all connected, or the other way.
All right. Okay.
All right. So let's add to our rules here to account for that. So our second rule is going to be to number number the carbons so that the substituents are closest to 1. So think about how we could have numbered this. Oh, wow, it's candy day.
Well,
That was immediate. What is it? Yeah.
Every time I get into the club, I think
I am
it's
so
candy.
sorry.
I suddenly look up and there's just candy everywhere. Thanks.
Thank you so much.
Of course. I know that.
Oops.
I'm so sorry about that.
That's all right. It's a little smashed, but I also dropped it again, so it's probably not your fault. I will wait so that I'm not talking with candy in my mouth at the moment. So there are a few ways we could have numbered this chain. We picked 1, 2, 3, 4 from left to right just because I knew the right answer, but we could have gone 1, 2, 3, 4. We could have gone 1, 2, 3, 4. This example on the board is maybe a better example. So if we say that this is the longest carbon chain, then we need to pick numbering it so that the substituents are closest to 1. What that means is we want to number 1, 2, 3, 4 so that the substituent is on 2, not 1, 2, 3, 4, because then the substituent would be on 3. See what I'm saying there?
Mhm.
Additionally, we need to make sure to have the longest chain. And this is a common mistake. If you see a structure written like this, it's easy to say, oh, well, that's the chain because it's going across left to right. But that's not the longest chain. That's only 3 carbons. The longest chain is this one or this one. So we're going to look for the longest possible chain, and we're going to number it so that the substituents are closest to 1. Okay. Then once we've done that, we're going to find all the substituents and name them. In this case, there was just one, so that's it. Let's look at a case where that's not the case. So let's look at this other example of a pentane isomer. Let's go through the steps here. What's the longest chain in this molecule? How many carbons are in the longest continuous chain? Just this one? Or you said this one? This. Yeah. Yeah, actually, it doesn't really matter where you count it in this case. It's just 3, any way you go. So let's go a different way just because it's the left to right is always obvious. Let's pick one. Let's pick a different one as long as it's all the same. Let's go 1, 2, 3. That's totally fine, right? That's also a 3-carbon chain. So we numbered so that the substituents are closest to 1. Well, in this case, it doesn't matter because they're always going to be in the middle. So now we've got to find the substituents. And in this case, there are 2. So there are 2 things that are not a part of the main chain. And they are methyl, right? They're methyl groups. So this one's going to, instead of saying 2-methyl, we have to account for the fact that there are 2 of them. What's a 3-carbon chain called? Anybody remember?
No, it's propane.
Propane, right? So then the way we account for that is instead of just saying methyl, we say dimethyl, meaning 2 of them. Dimethylpropane. And then when we do our numbers, each substituent gets its own number. Which means we're going to name this 2,2-dimethylpropane. We need 2 numbers for 2 substituents. So it's not just 2-dimethylpropane, it's 2,2. Each substituent gets its own number. These rules were all set up, they're called the IUPAC rule, International Union of Pure and Applied Chemistry. And they're set up to be unique. They're set up so that every different chemical will have a different name and only one kind of name. They will always, that way we will always know what we're talking about. We'll always know what structure we're talking about. Before this, compounds would always have just whatever name somebody wanted to give them. For instance, pentane was pentane, and then this was called isopentane, and this is called neopentane. So you just had to know all these different names, and sometimes compounds would be given names based on like what plant they came from, or what type of a thing they came from, or what country they were found in, or whatever. So it got very confusing because you just had to memorize every possible name. This way, all you need is a few rules, and you can get the name all the time. You can always name it and always get it right.
So you can just give like the name and ask us to write formula.
Right, so let's try that. I understand that, but it's a good exercise, so let's try it. I'm going to give you a fairly complex name, and we're going to take it apart and see if we can draw the structure from that name. Okay? Everybody ready? Okay. Whoops, hold on. 3-ethyl. Three-ethyl 4-methyl hexane. How are we going to deal with that? Let's see. So what do you think is the best thing to put down first if you're trying to get the structure from the name?
I think the structure 6H14.
That's not necessarily going to be right because that doesn't account for the substituents, right?
Yeah.
So the best thing I think to do first is to put down that longest chain, whatever that is. What is it in this case? Hexane. So how many carbons is that? 6. So we just write down 6 carbons in a row. We won't put the hydrogens in just yet. We'll do that later. So we'll put down 6 carbons in a row, and let's number them so we know what's where. So 1, 2, 4, 5, 6. Okay, now let's start putting those substituents in there. We know, so ignore that first one for now because we haven't talked about that yet. What does 4-methyl mean? What are you going to do about that?
That means that there are 4 side CH4.
Close, but it's CH3, but there's going to be 1 carbon coming off of carbon number 4. That's going to be our methyl, right? So if that's methyl, what do you think ethyl is? Yeah, 2 carbons. So if methyl is a 1 carbon substituent, ethyl is a 2 carbon substituent. So that's going to look like, we'll put it up just so we have a little more room. Right, 2 carbons in a row. So this is an ethyl substituent. Of course, it has hydrogens also. We just haven't put them in yet. And if the chains are long enough, you can have propyl substituents, butyl, pentyl, hexyl, whatever. You have that many of things coming off of another chain that's named accordingly. All right, so now we've basically got it. All we've got to do is fill in the right number of hydrogens. We've accounted for the main chain and each substituent. So now we fill in our hydrogens and we've got the full structure. So that's going to be 3 here, 2 here, 1 there, 1 there, 2 here, 3 there, 2 there, and 3 there. And if you're not comfortable just abbreviating them like that yet, you will after you get some practice at it. You can just draw all the hydrogens out like that. So that would be the full correct structure for 3-ethyl 4-methyl hexane. Yeah, so the total molecular formula here then would be C 9 H20. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons and 20 hydrogens. Oh.
See, on the ethyl group, you have
Yeah.
CH2 and CH3.
Right.
Down on G and no.
It takes practice.
This absolutely takes practice, yes. That's why we have
I get
a nice 100 or so homework problems to work on. Yeah, this takes a little practice. Once you've done it on a bunch of stuff, you know, it'll get less crazy. So let's look at one other variation that we can throw in here, because really this is pretty much it for these types of compounds. There's another class of compounds that are called cycloalkanes. What do you think that means? You had to guess. Yeah, like in a circle. So if you had instead of these straight chains, sometimes you can connect your carbons in a circle or a hexagon or whatever. Yeah, so here would be 6 carbons, and they'd then each have 2 hydrogens.
It looks like in the sugar phosphate sugar.
Yeah, right. So sugars are made of 6 membered rings like this, with oxygen in them. And we can't call this hexane because we already have a hexane. That's the straight chain. We can't name this from our rules because it doesn't really have substituents coming off. It's just that everything's connected in a circle. Right. So we would call this cyclohexane. It has a different name. That cyclo tells you it's in a ring. Also, you'll note this has a different formula from hexane. This is C6H12, so double the number of hydrogens is the number of carbons, whereas hexane would be C6H14 with those extra 2. You don't need those 2 now because you need to take them off in order to get the ends to connect to each other. So the carbons can still have 4 bonds. What is the smallest cycloalkane? Yeah, C3. What would that be called? Yeah, cyclopropane. Can't get any smaller than that, or you just have a line. It's not cyclo anymore. So you can go from cyclopropane all the way up to as many carbons as you want, and you just put the cyclo in front of it. So let's try a name with one of those. Sorry, go ahead. Wait, hold on.
So it'd be C3H6? Yeah, obviously.
Right. So what if you have a structure like this? What do you do about that name? So, yeah, you're all kind of doing the right thing. If there is a ring use it for the main, what we call the chain. In other words, don't say that the longest chain is 1, 2, 3, 4, 5, 6, 7, 8. That's not right because of the ring here. So we use this ring as our main chain, and then that makes this and this substituents. So see if you can name it from that then.
Then if I name it, you don't have to consider now the number of the row, number 2, number of the carbon.
We do, because we have to know which carbon has which substituent.
No, I mean like
Yeah.
we named it following the second or the third carbon.
Mhm.
Right. Now it's the second.
So you have to number it, and you number around the ring in such a way that the substituents get the lowest numbers.
I think I get it.
All right, what do you got?
So like 1 is that methyl.
Okay,
Well, so you gotta start off with cyclohexene.
well, that's going to be at the end, but
1 methyl.
yeah.
2. Two.
Yeah.
Methyl. Methyl.
So the tail and
Yeah.
and cyclopentane pantene.
Yeah, there you go, cyclopentane. So our main chain here is going to be 5 carbons in a ring together. So that's, I'm going to give myself a little more room here. So that's cyclopentane. And then we have to number it in such a way that we get the smallest numbers on the substituents. Now, there's actually 2 choices here. We could go 1, 2, or 1, 2. In this case, you go 1, 2 this way. So 1, 2, 3, 4, 5. Because ethyl starts with E, methyl starts with M, so the E comes before that. The E gets precedence over the M. But it doesn't really matter. Those sorts of distinctions we're not going to focus on in this class. So this could be 1 ethyl, 2 methyl cyclopentane.
So what about the second part, the methyl that's on the ethyl?
That's part of the ethyl. The fact that there's 2 carbons there makes it ethyl. So those 2 things together are an ethyl group. And that accounts for everything in this molecule. All right, let's try another one. Also, I changed my mind. This will not be on the exam. We should not put this on the exam. We need more time. So the exam will go through the acids and bases chapter and the nuclear chapter, but not this. But yeah, solutions, acids, bases, nuclear, and stuff from before. All I said was not this.
No, it was just a second ago.
Not the stuff from today. We need more time. Right. So we'll have a quiz on this stuff the week after the exam, and then this stuff will be on the final.
Okay.
Right. Okay, let's try another one. All right, see if you can come up with a name for this one. Got it? Yep. Okay. Another couple minutes. Keep thinking about it. You may need to look up something on the chart there.
Is this a cyclo?
Is it a cyclo anything?
Yeah.
Is it a ring?
No. And no.
Right.
It's a no name pro. Something. Or you're trying to look for like butane, that kind of name?
Hmm.
Non. Propylene?
You have to first find the longest chain, right?
Yep.
And if you
I mean, it's pretty much all equal if you look at it though.
You still have to find the longest chain.
See if you can come up with a name. Write down a name, and then we'll see what kind of names you came up with. Doesn't have to be right. Just something. I'm gonna start with.
Is he was showing us that
Us finding the longest continuous carbon chain, can we do the top row, the
Mm-hmm.
like,
Starting like here,
yeah,
like those three
those three are then going down or
down here, and then where?
down again?
Down again,
Can you?
and then over.
Can you?
And the chain, does the chain have to take like everything, or does it just take one? I understand how the chain.
It can go wherever it needs to get the most carbons in it without jumping.
Oh, so it looks like that.
Yeah.
So that would be it. Let's see.
Right. So it looks like y'all found the right longest chain, which would be this one. 1, 2, 3, 4, 5, 7. Right? Because if you go this way or this way,
You're missing
you're,
4.
you're only going to get 6 instead of 7. Okay. So if you get that far, see if you can get the rest of the name.
7 is 17.
Sound like a strange language.
Yeah, it is. It is a different language. That's why it takes practice. Just like a different language. All right. So what's the longest chain named here then? Heptane. Heptane. And what are substituents here then? Substituents are anything that's not part of the main chain. So that's going to be this. Yeah.
So it's 4 ethyl heptane.
Right. 4 ethyl heptane. That should be one word. 4 ethyl heptane. Good.
So for both of those names, we just count
Try another.
Three or five? Three.
All right, see what you can do with this one.
No, after you want to.
Makes sense.
That's what we did last time.
Can you, when you're figuring out the longest chain,
Mm-hmm.
the top CH2 and CH2, can you just use the CH3, go to carbon and go off to the left?
Mm-hmm.
You don't need to split it up.
We didn't split it up.
You just like take your chain, the starting chain, set it
Yeah,
in between the two, or can you go the whole,
like this, like this,
like from the top,
here,
yeah, to the right? Am I right?
there,
Yeah, from there.
to there,
No, from there down to carbon to the left.
this way, like
Yeah.
that. Yeah. Yeah, that's right.
Okay.
3,
So
5 methyl. 3.
All right, anybody want to try a whole name?
3
3-methylpropane, what do you think?
3, 3.
No.
3,3-dimethyl pentane. Okay, others?
Sorry, I meant 3-ethyl protein. Pentane, sorry, pentane.
Okay.
Three.
All right, so they're correct. Let's look at this again. So when we number this, we find the longest chain is here, right? In this case, it doesn't matter where we start the numbering from one side or the other because these are in the middle. Constituents are in the middle. So we can go 1, 2, 3, 4, 5, or we could have gone 1, 2, 3, 4, 5. Same thing. But that either way we go, that makes this a pentane. Okay, so then the next question is what to do about these substituents. These are two separate substituents, right? They are not connected to each other. So that makes it, right. So that makes the substituents dimethyl, meaning two methyls. So 3,3-dimethyl pentane. Because we have to account for both of those. It can't be an ethyl because that assumes that they are connected together. So for the last thing before we go, let's look at that. Let's look at the name of, at this name. Three-ethyl pentane, which is very similar. See if you can draw a structure for 3-ethyl pentane and see how it's different from what we just did.
Can't figure out how to do the two remaining hydrogens. That's what I'm saying.
The what? The hydrogens?
Yeah.
Where?
Well, can I think it's with carbons? I'm still kind
Where's it? So you have 5 carbons in a row. And then you get that one.
That's the dimethyl. See how we can make the ethyl different.
Two.
Right. So normally I would just write this across like 5 for the pentane like that. I'm going to write it a little differently just so we can compare it to this one. I'm going to keep the same chain that we had in the first one. So there's my 1, 2, 3, 4, 5. So then ethyl would be 2 more carbons coming off of that third one. So there's my 5-carbon chain. There's my ethyl substituent. And there's various ways you could write this and be correct. You could write it all the 5 in a straight line and then the ethyl coming straight down or up or whatever. But if you have 5 carbons in a row with then 2 in a row coming off that 3rd carbon, then you have the right structure. All right, so practice this. We won't talk about this again until after Thanksgiving, so after the exam. So I'll see you Monday for our final lab of the year, the organic compounds lab, where we'll deal with some of this stuff in a lab environment. And then the week after that, we will have our exam. And then there's one more week and the final. That's it. So we're almost done.